Okay, so this is the second video for section 3.6. This is where we're going to talk about complex zeros of polynomials. Now here we have the problem. Find the zeros of f of x equals x squared minus 2x plus 5. This doesn't look factorable to me. So what we're going to do, and in fact, since we're talking about complex zeros, it's obviously not going to be factorable, right? So what we're going to do is we're going to set up the quadratic formula. I'm just going to take note of what a, b, and c are. So this is opposite of b plus or minus square root b squared minus 4ac all over 2a. This ends up just being positive 2 plus or minus the square root of, let's see, in here I have 4 minus 20, that's going to be negative 16 all over 2. Now the square root of negative 16 is the same thing as the square root of 16 times the square root of negative 1. Oh, and keep in mind we're finding our x-intercepts here, right? So this is an x equals at the beginning. Let me find where my mouse went. There we go. So now, this is 2 plus or minus, the square root of 16 is 4. The square root of negative 1 we defined to be I. And when I carry out this division, I get 1 plus or minus 2i. So let's look at this thing called the fundamental theorem of algebra. This question is, the question that would lead us to this is, can there be any polynomials that don't have any zeros? And the answer is no. The fundamental theorem of algebra says a non-constant polynomial f with real or complex coefficients will have at least one real or complex zero. So as long as this function is non-constant and it's a polynomial, then this fundamental theorem of algebra applies to it. And importantly, we have this thing called the complex factorization theorem that's very, very useful. If f is a polynomial with real or complex coefficients with degree n is greater than or equal to 1, then f has exactly n real or complex zeros, counting multiplicities. So in other words, an nth degree polynomial has n roots when you count the multiplicities. And this is just a more formalized kind of rephrasing of this thing at the bottom. So let's look at an example here. Do I have a graph? Yeah, I do have a graph. I did graph this already. So the first thing that we want to do for finding all the real and complex zeros of this given polynomial is we want to use our rational roots theorem to find all possible rational roots here. So all of the factors of 1 are just 1. All of the factors of 12 are 1, 2, 3, 4, 6, and 12. So this means that my possible rational roots are plus or minus 1, plus or minus 1/2, plus or minus 1/3, plus or minus 1/4, plus or minus 1/6, and plus or minus 1/12. These are my possible rational roots from the rational roots theorem. At this point, I want to graph this function, which I've already done here. And I want to see if any of these possibly make sense on this graph. Let's see. I have something going on between 0 and 1. It looks like this is maybe x equals 1/2. This is maybe x equals 1/2. And I have something going on right here between 0 and negative 1. This would be either x equals negative 1/3 or negative 1/4. But let's see, this is broken up into 1, 2, 3, 4, 5 pieces. To me, this looks like this is closer to x equals negative 1/3. Also, notice that this x equals 1/2, if this is a root, right, then it probably has multiplicity 2, as the graph touches the x-axis and bounces off. So we're going to test to see if I have a root of x equals 1/2 with a multiplicity of 2. And we're going to test to see if I have a root of x equals negative 1/3. So I need to grab that polynomial and I need to set up some polynomial division. Let's see. So I'm going to put 1/2 in the box. We're going to divide by this one twice since we think it has multiplicity 2. My coefficients here are 12, negative 20, 19, negative 6, negative 2, and 1. The 12 comes straight down. 12 times 1/2 is 6, plus negative 20 is negative 14, times 1/2 is negative 7, plus 19 is 12, times 1/2 is 6, plus negative 6 is 0, times 1/2 is 0. Negative 2 plus 0 is negative 2, times 1/2 is negative 1. 1 plus negative 1 is 0. I get a remainder of 0. So this is a root. X equals 1/2 is a root. Let's check to make sure it has multiplicity 2. And to also further reduce this polynomial, let's see. 12 comes straight down. 12 times 1/2 is 6. Negative 4 plus 6 is negative 8, times 1/2 is negative 4. 12 plus negative 4 is 8, times 1/2 is 4, plus 0 is 4, times 1/2 is 2, plus negative 2 is 0. Yeah, so I have x equals negative 1/2 with multiplicity 2. Now, let's test what I have left here for that 0 that we thought of x equals negative 1/3. Negative 1/3 goes in this box. My coefficients here are 12, negative 8, 8, and 4. 12 comes straight down. 12 times negative 1/3 is negative 4. Plus negative 8 is negative 12. Times negative 1/3 is positive 4. Plus 8 is 12. Times negative 1/3 is negative 4. Plus 4 is 0. I get a remainder of 0. So x equals 1/3, or x equals negative 1/3 rather, is also a root. So far, I've been able to factor this polynomial to say that this f of x is equal to x minus 1/2 squared, because if x is equal to positive 1/2, then the corresponding factor here is x minus 1/2. And this is squared because it has multiplicity 2, times x plus 1/3 times 12x squared minus 12x plus 12. Or I can factor this 12 out and say that this is 12 times x minus 1/2 squared times x plus 1/3 times x squared minus x plus 1. And now I can use the quadratic formula to find these remaining zeros of this quadratic at the end here. My quadratic formula will be, let's see, opposite of b plus or minus square root b squared minus 4ac all over 2a. This is negative 1 negative negative 1 is positive 1, so this is 1, plus or minus 1 minus 4, that's going to be the square root of negative 3, all over 2. This is going to be 1 plus or minus I times the square root of 3, all over 2. So the roots of this function are x equals 1/2, x equals negative 1/3, x equals 1 plus I root 3 over 2, or you could write root 3 times I over 2, and 1 minus I root 3 over 2. So this function could be fully factored as f of x equals 12 times x minus 1/2 squared times x plus 1/3 times x minus 1 plus I root 3 over 2 times x minus 1 minus I root 3 over 2. And when we factor something in this way, we say that this is factored completely over the complex numbers. Meaning that you cannot factor this thing further. If we wanted to factor this over the real numbers, we would have just stopped at that 12 times x minus 1/2 squared times x plus 1/3 times x squared minus x plus 1. Because x squared minus x plus 1 has no real zeros, we say that that thing is an irreducible quadratic. And that's it for our lecture on complex zeros